Okay, well, this week's seminar speaker is Dr. Andrew Dix. He's got his undergraduate degree at the University of Wales in Swansea and his graduate work at the University of Durham. And he joined the University of Toronto Chemistry Department in 1997. He has research interests in undergraduate laboratory instruction that involve designing novel and stimulating experiments, particularly those that showcase green chemistry principles. In 2006, he became the Associate Chair for Undergraduate Studies, and he has won the following pedagogic awards: the University of Toronto's President's Teaching Award, the Canadian Institute of Chemistry National Award for Chemical Education, and most recently in 2011, the American Chemical Society Committee on Environmental Improvement Award for incorporating sustainability into chemistry education. And he is the editor of the recent green chemistry teaching textbook, Green Organic Chemistry in Lecture and Laboratory, which is published by the CRC Press. And with that, I would like to introduce Dr. Andrew Dix, who is going to present on Catalysis as the focal point of green chemistry teaching. Thank you, Andrew.
Okay, well, thanks very much for the introduction, Bob, and thank you very much for the invitation to speak to you this afternoon. I guess I should do a sound check before we go any further. So can everybody hear me okay? Good, and can see me okay and can see the slides okay?
Yes, they're excellent.
All right, good. So I can imagine that anybody in the world can be invited to give this sort of seminar, and I'm very privileged to be your speaker this afternoon. It might look like I'm in my office, but I'm not. I'm actually at home today. This is a little bit of a nicer environment than my office. We were talking for a few minutes before we started to come online, and I was saying to Bob that the weather was absolutely lousy here, so it saved me a journey to work, and I don't have a webcam in my office, so I'm working from home today. I'm hoping that you won't see a 3-year-old boy burst into the room in the next 50 minutes or so, because my son is downstairs with my wife, and hopefully he'll stay there for the duration of this presentation, because he can get quite noisy at times. Just to give you a little bit more of a perspective on above and beyond what Bob just introduced me there, I was hired as a faculty member at U of T in 2001. We're a pretty big department. We typically teach 1,500 students first year chemistry, and we're quite unusual in that we teach a single semester of organic chemistry in first year, which I don't think hardly any American universities would do. Quite a few Canadian schools do that now. So we have a lot of program students. We typically have across the department something like 500 program students taking some sort of chemistry program of some kind. It might be a minor or a major or a specialist program, which is essentially the equivalent of a major program in the US, where students spend about 2/3 of their time taking chemistry courses and 1/3 taking electives in sciences and other departments as well. We are part of the Faculty of Arts and Science, which is a very, very diverse faculty. It's got 29 or 30 different departments. So you can imagine that it gets a bit interesting when we're compared in funding situations with departments like English and history and so on. It gets quite interesting from that perspective. What I thought I would do today is to talk a little bit about some research that we've been doing from a pedagogical perspective in the context of green chemistry. This is something that we're very interested in at U of T, and we've tried to develop a bunch of experiments and some new lecture modules which really showcase cutting-edge methodologies in green chemistry. We think it's very important to teach undergraduates about the fundamental principles, not necessarily in a standalone green chemistry course, but to weave green chemistry into existing courses. That's the approach that we have decided to take for a number of reasons. So if I start talking about specifically some of the slides now, the first thing that I really need to do is to acknowledge the students that have done all the work that I'll be talking about today. in my position in the department, I'm not allowed to supervise graduate students. I'm actually a teaching faculty member, which means that my major role at U of T is to teach lectures and laboratories right across the undergraduate curriculum. I actually teach an upper level physical organic course which graduate students can take, but I'm not allowed to supervise graduate students. I'm not appointed to the School of Graduate Studies. But I am strongly encouraged that teaching faculty members, there's 8 of us in our department, it's strongly encouraged that we do actually supervise undergraduates. And that can be in more of an applied research project, or it can be in a more pedagogical project. And the latter is what I've really been involved in for the last 10 years or so. The names of the people that you see up there are essentially all undergrads. And the people at the top left-hand side were doing 4th-year research projects with me. This is essentially for the honors thesis research. The people at the bottom left-hand side here are people that were doing a 2nd-year research project. We have quite a big commitment in the university to offer research projects for students that have just finished their 1st year and want to get a taste of what research is like. So those students are listed there. There are some summer volunteers, some people that are listed as chemistry teaching fellows, upper level students who receive some funding to do some academic research, and just a little bit of a mention for the funding organizations there as well, in order to pay for chemicals and equipment and so on. So everything I'm talking about today is down to these folk, and I'm just acknowledging them at the beginning in that respect. So the main focus of what I'm going to get into is about a new course that we designed 4 years ago now. We're actually teaching the course at the moment for the 5th time. And it's a course that we call Organic Synthesis Techniques. So although there's a lot of green chemistry within the course, we don't call it green chemistry. The green chemistry is really woven into the course. This course really came about because for a number of years built into it, and the lectures and the labs did not coordinate at all. So generally the person teaching the course the lectures would not be running the labs, and it was proving pretty difficult to blend the lecture and the lab. Education, a number of papers were published online, and ours was one of those, where we highlighted the nature of organic synthesis techniques and how it ran and so on. So hopefully in the next 6 months or so, a short description of the course will be profiled in the Journal of Chemical Education, as will the other papers that were discussed as part of the ConfChem online conference. So that's the resource for you if you're interested in looking at this in a bit more detail after today's lecture. So with that in mind then, we need to really be clear, and obviously we make this point with students, why we would bother talking about catalysis. And this is why, one of the reasons how we sell it to students. If you look at Nobel Prizes over the last decade or so, there are 9 researchers who have been acknowledged for catalytic reactivity in terms of the chemistry Nobel Prize, going back to 2001 with Knowles and Noyori and Sharpless, 2005 the metathesis methods Schrock, Grubbs and Chauvin, and then more recently, and this is actually an area that we profile a lot in organic synthesis techniques, is particularly the palladium cross couplings of Heck and Suzuki, and also the nickel cross couplings of Negishi. So it's really cutting edge stuff, and we know that as instructors, but it's emphasizing the point that the students are often doing some Nobel Prize winning chemistry in their undergrad labs, and that's obviously very important for them to realize the relevance of this and the importance of these types of reactions in industry, for example. So that is very easy to do in this type of course, because not only can they do the experiments in the lab, emphasizing the green chemistry aspects of them, but it can be emphasized in the lecture as well, where the reaction mechanisms can be discussed, and that helps them particularly with the composition of their lab reports. So they show a good understanding of the reaction mechanisms there. So what I thought I would do is walk you through a few examples of actual experiments that we've designed, and the sort of green aspects of them and the catalytic aspects of them, and other things as well. So we very much believe that students should be doing reactions to make products that are of some sort of relevance to them. And 7 or 8 years ago, we designed a two-step synthesis, starting with paramethoxybenzaldehyde here. We designed a two-step synthesis of the compound down here on the far right-hand side, which is a sunscreen analog. And this is not a compound that is present in any commercial sunscreen like Coppertone, for example. They tend to have longer hydrocarbon chains as part of the ester here, octyl chain or 2-ethyl hexyl chain tends to be there in a number of sunscreens. We targeted this particular compound to be made, and it was made by a two-step reaction, two-step process, where firstly the students took malonic acid here and condensed it with the aldehyde under conditions of organocatalysis. So they use just an amino acid, beta-alanine, to help this reaction along, and they form the cinnamic acid in very, very good yield, typically. And we thought, although we designed this something like 8 or 9 years ago, we weren't really emphasizing the catalytic feature of the reaction very much back then, but it seemed to be a good opportunity with the new course in place to talk about the way in which beta-alanine is acting as an organocatalyst here. They then did, from our original design, just an esterification reaction, and this is not particularly green. It's not done under green conditions, really, just forming the final product here. But essentially, when we have a reaction that's not very green, we get the students to justify why. So in this case, they're using DMF as a solvent, which is not particularly nice, and ethyl iodide and so on. So that was our original two-step synthesis, starting from paramethoxybenzaldehyde there. About 3 or 4 years ago, when we started teaching this new course, we added on this first step, where students do a phase transfer catalyst reaction, starting with the parahydroxybenzaldehyde, and they use the phase transfer catalyst aliquat 336 in the presence of iodomethane. And this reaction is just done in water. The transformation takes about an hour or so of refluxing in water. There's an organic extraction after that, but fundamentally the first reaction is done under aqueous conditions, and you have the aliquat there in catalytic quantities. So this is now used then, 2 of the 3 steps. This has been a mainstay really of our new course for 4 or 5 years, and the 2 steps were in place for at least 4 or 5 years before that. So this is one of our banker experiments that we like to have in place. The overall sort of yield for this 3-step synthesis is typically in the range of about 40 to 50%. So the first 2 steps are very, very high yielding, both of them. The 3rd step, typically students will get sort of 60 to 70%, something like that. So that brings the overall yield down. But there's a lot of aspects of green chemistry to be talked about here, in terms of not only the catalysis, but also doing reaction under aqueous conditions. What we want to get away from is the idea that often students hear about in introductory organic courses, where reactions can't be done in water. They just won't work. We kind of often, as instructors, I think, give that impression, particularly when we're talking about organometallics and Grignard reagents. It's very clear that using water is almost impossible, but it's important for students to appreciate that a lot of research is being done now on reactions under aqueous conditions, and a number of those reactions actually work better in water than they do in a traditional organic solvent. So this is a nice opportunity to emphasize that. For people that are interested in this in a bit more detail, our original Journal of Chemical Education publication is listed there at the bottom. So the first 2 steps are outlined in the paper from 2004. And this was actually a 4th-year undergraduate student who worked on the initial design of this experiment he designed it in 2001. So there's a bit more information there. So that's where we can talk about organocatalysis and phase transfer catalysis. A second example, or a second type of experiment that we always tend to run in the context of this course is palladium catalyzed cross coupling. And here's an example of a Suzuki reaction that we have designed. So this is tying directly into the Nobel Prize winning work of a couple of years ago. And in this situation, students are forming 4-phenyl-phenol, so the compound here on the right-hand side. And that is interesting because it's the nucleus of a number of non-steroidal anti-inflammatory drugs. So this compound here is diflunisal, and you can see the 4-phenyl-phenol backbone of the molecule. So we have the opportunity there to tie in with the biological activity. I should have said on the previous slide that with the sunscreen, we spend a lot of time talking about UV light absorption and measuring the UV spectrum of that type of compound. Here we can get into the biological activity of these sorts of drugs. The majority of our students that are in specialist programs are in a biological chemistry specialist program. So they are particularly interested in the mode of action of these types of compounds. So we have a nice hook with making them in the lab to tie it into their medicinal properties. And this is a very, very simple reaction that we modified from the primary literature, where the Suzuki cross-coupling is just done, again, under aqueous conditions. There's no organic solvent here at all for the reaction. Students just use a small amount of palladium on carbon, so that there's no ligands involved here. And that's just a 30-minute reflux, and the product there is typically will just precipitate and just can be recrystallized from an alcohol-water mixture. So we're not using any solvents that are particularly nasty in the reaction at all, or the workup. So that works very nicely. Typically the students there, I've noted that the yield is around about 65%, something like that. This is done on a micro scale. So the students are maybe making 100, 150 milligrams of this product. Throughout the course, we try and get students to work at a number of different scales. So they do some work at a really, really small scale, where they're making maybe 100 microliters of a liquid, but they move up to making about 5 grams of a solid as the biggest scale. So they're working certainly micro. The sunscreen synthesis is really on a semi-micro scale, and larger scales are done as well. We think that's quite important to expose them to different scales using different types of glassware. So this experiment was picked up by the ACS, and they've run this at their summer school on green chemistry and sustainable energy for the last few years. And this is based, again, their work is based on the publication that we put out in 2008 on this particular work, which we just call Greening Up the Suzuki Reaction. So this summer school is an opportunity for graduate students and postdocs to go and learn about principles of green chemistry from experts in the field. And it's been held for a number of years in Colorado, but it's also been held up in Canada at McGill University in Montreal as well. It's a nice thing to look into if you're there today as a graduate student and you're interested in learning more about green chemistry. So that works well. We've actually, I don't have any slides to show you, but we have similar types of reactions where students do a Heck reaction and they form a conjugated alkene under similar types of conditions where they use palladium chloride as the catalyst there. And we've recently designed a Sonnecker-Shearer reaction as well, where students make an internal alkyne by the same type of cross-coupling reaction. And those reactions, the Heck reaction is done in pure water. The Sonnecker-Shearer reaction is done with an organic co-solvent present. But it's nice to use this type of chemistry to showcase the aqueous reactivity and obviously the catalytic properties. I should mention here that the catalyst can be recycled quite nicely too. So the amount of catalyst they only need is only 2 or 3 milligrams. That can be gravity filtered off at the end of the reaction, and it can be reused quite nicely. So that's another aspect that can be emphasized with students if necessary. So that's a second example. Here's a third one that we've worked on. Again, we've run this type of reaction for a number of years, but not really talked about it in the context of it being catalytic. So this is an oxidation of a primary alcohol, geraniol, to geranial. So it will go to here under the reaction conditions, it will form the aldehyde and not the carboxylic acid. This is using a ruthenium 7 catalyst called TPAP. And the structure of TPAP is there in the center of the screen. TPAP is very expensive, or relatively expensive to buy. It's about $200 for a gram, something like that, if you buy it from Sigma Aldrich. You can make it really for a fraction of that cost if you just buy the necessary reagents. You need ruthenium trichloride. That gets oxidized, and then you add the tetrapropyl ammonium salt to it, and the TPAP precipitates as a black solid. It ends up being, and actually by coincidence I made a couple of grams of it yesterday because we will run this experiment in a couple of weeks. It only ends up being about $1 or $2 per student if you prepare it yourself. It requires 4 or 5 hours to prepare, but most of that is just unattended stirring time, so it's not really an issue to make it. TPAP can be used in a catalytic amount just to oxidize the geraniol to geranial, and I've tried to tie this into real-world relevance in the sense that geranial smells like roses and geranial smells like lemons, so you can immediately know if the reaction has worked in the undergrad lab because you have the very characteristic citrus odor. And this reaction we do on a pretty small scale. Students would only make maybe 100, 150 microliters of geraniol, which is a liquid, but you can immediately tell if it has worked by doing, I guess, nasal spectroscopy, just by smelling the compound and knowing that it's there. This is an interesting experiment to talk about with students in context of green chemistry, because although you have a catalytic oxidant, you have to have a co-oxidant in there, which is NMO, N-methylmorpholine N-oxide, and that's in there in stoichiometric amounts. You also, although it's pretty mild conditions, you just stir everything at room temperature for half an hour. The reaction is done in a mixture of dichloromethane and acetonitrile, and they're not particularly green solvents, either of them. So this is actually a very useful example to say to students that we have some green features here, but it could be greener. And this is a more traditional way of doing a TPAP oxidation. Students, if they look in the recent literature, can see examples where researchers have tried to green this methodology up a little bit, and they've used oxygen as the co-oxidant, molecular oxygen, and they've done the reaction in an ionic liquid, for example. So we try and use this to our advantage by saying to students, this is not a perfectly green synthesis, and you will not see a perfectly green synthesis at any time, but it's a good example to say, well, can you find ways that it's been done in a greener fashion? We have actually tried to do it in the lab with molecular oxygen as a co-oxidant. Didn't work very well. If we could get that to work, we would run it that way, but that doesn't seem to work too well. So this is, as I've mentioned here at the bottom, a nice opportunity to get into shortcomings, and it's important that students appreciate that green chemistry is not all or nothing. It's not a case of having something that is green or isn't green. There are shades of green. And this has certainly got some green features to it, but it could be greener. And if you use it in that kind of way, it tends to be quite productive, I think, with students. So that's another transition metal catalyzed reaction. I thought I would spend a little bit of time talking and show you a few slides about another approach that we've taken. And this is in the context of a very old reaction called the Bonelli reaction. And you can see from the date up here that the reaction is well over 100 years old now. It's had a little bit of a renaissance in the last decade or so because people have have realized that multi-component reactions are inherently green from the perspective of atom economy. So Bonelli obviously didn't realize this back when he discovered this type of process, but if you just take an aromatic aldehyde and a beta keto ester and urea, so very cheap, readily available starting materials, and you heat them up in the presence of acid, then you can form this type of structure here at the bottom, which is a 3,4-dihydropyrimidone. And it's amazing that this works, because mechanistically it's quite complex, and you can write different mechanisms for how this is actually going to proceed. The sort of structure that you have here in the product is analogous to a dihydropyridine, whose structures here on the right-hand side, one that is commercially available as an anti-anginal drug is called nifedipine. So nifedipine and other dihydropyridines can be made by Hansch synthesis, which is also a multi-component reaction. We have actually designed one of those for the undergrad lab. I'm not going to talk about it today because it doesn't have a catalytic component to it. It doesn't actually need a catalyst, but the biological relevance we emphasize to students here is the dihydropyrimidones also have interesting medicinal properties, and some of them are anti-anginals, but there is a structural relationship to the dihydropyridines over here as well. So nifedipine is marketed there. So this is the way in which the reaction was performed for a long time. This is essentially Bonelli's first synthesis of it that was reported in 1893. About a decade or so ago now, 2001, David Crouch, who is at Dickinson College in Pennsylvania, published an article in the Journal of Chemical Education where he took Bonelli's original reaction and really scaled it to work very well indeed in an undergrad lab environment. So he took the same 3 starting materials that you saw on the previous slide, and he heated them for 90 minutes in the presence of an acid catalyst and just in ethanol. And from that article, his average kind of yield was close to 60%. It was done on a micro scale. And from a green perspective, we'll get into some of the aspects of that in a few minutes. But that was quite intriguing for us a number of years ago, because we had noticed in the literature that all sorts of new synthetic methods had popped up to make this kind of compound that deviated quite significantly from the traditional synthesis that we have on the screen there. So this was very nicely designed for an undergrad lab environment, and it could be run in a small class or a big class. It's not requiring lots of sophisticated glassware. As I mentioned, the starting materials are all cheap and readily available. Mechanistically, it's challenging, but students can have a lot of fun pushing curly arrows to try and explain how the product is formed. What we wanted to try and do was look at the more, shall I say, modern methods of making these Bonelli products and try and incorporate one of those into the undergrad lab and get students to do a metrics analysis between the newer method, the modern method, and the more traditional method that Crouch had designed a few years ago. So we spent a bit of time, and students researched, that's undergraduate students working with me in research projects. They looked at the literature and came up with some ideas as to which might be the sort of better methods to try to see if the Bonelli reaction would work. They mainly varied by changing the catalyst. So a lot of Lewis acid catalysts have been looked at in the last decade for this type of reaction. And as I say, what we wanted to do, the goal here was really to take a modern method, compare it with the traditional method from a green perspective. That can be done qualitatively for sure, but it can also be done quantitatively if you're looking at exactly the same reaction. And we tried this in a couple of different ways. We've had, on occasion, depending on the size of the class, we've had one student doing both of the reactions themselves if the class has been smaller. If the class has been larger, then one student will do one reaction by method, the more traditional method, and another student will do the reaction by one of the newer methods. So what we settled on, we tried a number of different conditions. We spent a bit of time trying different things out, and we settled on the same reaction. From a modern perspective, we started using zinc chloride as a Lewis acid catalyst. And it turned out that if you did this, then you didn't need a solvent for the reaction at all. And you could just heat the mixture for about 15 minutes or so, just in an Erlenmeyer flask. And again, this is done, you'll see the scale in a minute or so. It's done on a few millimole scale. That can be compared with the more traditional method where it's much more energy intensive. We said that you needed to reflux the reactants in a solvent, ethanol, for about an hour and a half. So the yields tend to be comparable or often a little bit better. If we go back to the more traditional method, I mentioned there from Crouch's paper and from our own observations, the yield is just below 60%. I've mentioned here that it's typically a little bit above 60% in terms of the more modern method in the absence of solvent. So this is an example of solvent-free reactivity, where the reaction goes just as well, if not better, without any solvent present. Certainly a much shorter reaction time. And that's just a proton NMR. That may not look very good on your screen. It doesn't look fantastic on mine, but that's just a student NMR example, and it just shows that the product is formed very cleanly. Apart from the aromatic protons in here, you don't have any overlap of any of the other signals. So you can quite easily see that the product has been formed, and you can pick up any impurities that are present very, very easily indeed. It's a nice proton NMR, and students tend to get the product from the modern synthesis very, very cleanly. So what we want students to do in this regard is to compare the methodologies, and as I said, you can do this quantitatively and qualitatively. From a quantitative perspective, an interest industrially from this type of reaction is the fact that its atom economy, its intrinsic atom economy, is very, very high. So if you look at the breakdown of the reaction here, and we highlight the portions of the molecules that end up in the final product in red, you can see that in terms of the molecular weights, the product there has a molecular weight of just over 260. The only byproduct of the reaction is water. So 2 molecules of water are generated here. No matter how you do the reaction, the conditions, the intrinsic atom economy, if you look at it just based on the molecular weights, the intrinsic atom economy is nearly 88%. And because it's a benign byproduct, that's really pretty good in terms of a metric perspective. Now, we spend a little bit of time trying to emphasize to students that the intrinsic atom economy that Trost came up with a couple of decades ago only tells a very, very small part of the story. And that really we should be looking at experimental atom economies which take into account the amounts of substances that we have in the reaction, because you may have a big excess of one reactant that doesn't actually get used up and doesn't get incorporated into the desired product. And that's a little bit of departure for students in many ways, because they haven't thought that way before. So what we ask them to do then is to look at the 2 methods they've performed in the lab, the traditional and the modern method, and to do some calculations. And this is just a simple breakdown of the traditional method to work out the experimental atom economy. You can see here, if you look at the number of millimoles of the 3 reactants, that the ethyl acetoacetate is in an excess. And because of that, if you do the calculation of the experimental atom economy, it comes out to be just short of 72%. Now that is down from 88% if you just look at it intrinsically in terms of molecular weights. So that's an interesting feature. If the student does the same sort of analysis for the modern method, then you'll actually see that the reaction is solvent-free, because the two liquids in there are benzaldehyde and ethyl acetoacetate. They're equal millimoles of those two. There's a little bit of an excess of urea, and the zinc chloride is catalytic. If they do the calculation there for the experimental atom economy, the number is almost exactly 80%. So it's about 8% higher than the traditional analysis. If we quickly just look back at that, the traditional number comes out at below 72%, and the modern number comes out at almost 80%. So that's quite interesting for students. It's not something they've ever thought about before in terms of evaluating a reaction. Often students coming from introductory organic classes have what I call a yield is everything mentality, where they just judge a reaction purely on the percentage yield that they got, and if something gives you a 90% yield, no matter what the atom economy is, it's a fantastic reaction. So we're trying to move away from that here, and not doing a really complex quantitative analysis, but at least thinking about things in terms of doing some rudimentary calculations. And then if we have actual chemical yields for the reactions that the students have undertaken, we can simply calculate the ultimate measure of the reaction efficiency, which takes into account that yield and the calculated experimental atom economy. So if they do that, they see that there's about a 7% difference typically between the two. So the modern method wins out. If you're looking at this quantitatively, obviously you can factor in qualitative aspects of the reactions, such as the reduced energy usage for the modern method versus the traditional method, the fact that the modern method is solvent-free. One thing is that we're not recycling the catalysts here, so the zinc chloride is not really recoverable and can't be reused. But again, we use that as an example, getting students to think about what improvements you could possibly see in this sort of chemistry. So I wanted to just briefly talk about some student-driven experiments, one in particular where we're getting people to think more on their own 2 feet about how to do synthetic reactions. And in this regard, an experiment that's worked well over probably about 6 or 7 years before we started the new course is to ask students to make this kind of compound here, an azelactone, starting with an ethyl ester or methyl ester of glycine. And these are chosen because A, they're very, very cheap, and you can buy large quantities, which is important if the class is quite big. And B, the starting material does not look particularly like the product, although you can see the sort of amino acid unit in the central azelactone ring here. What we can do is play about with the structure of W, X, Y, and Z, so that each student in the class, if the class is about 40 students in size, each student in the class can have a unique derivative. And what will work practically for one student may not work very well for somebody else, even though there's a subtle difference in the nature of the substituents on the aromatic rings. The students have to plan this synthesis, and it's checked by myself for safety and for cost. So I say to them that I'm not going to let you use a catalyst that costs $1,000 for 10 milligrams, but we may be able to use other catalysts. It's not checked to see if it will work or not. So I don't tell students if I think it will work or not. They have to start things and troubleshoot and do that in the presence of myself and the teaching assistants in the course. The compounds here are Alzheimer's disease drug candidates. They've been screened for their ability to treat Alzheimer's disease. So that has an interesting backstory to it. What we do here is not demand that green strategies are incorporated into the plan, but we give bonus marks for using more greener approaches and justifying the greenness, and not just saying, well, I did a reaction in water, so that's a green improvement. There needs to be a bit more of a justification than that. And this has been quite an interesting exercise, because as the literature has been updated over the last few years. Students have come with lots of new ideas on how to make these compounds and how to incorporate green chemistry. Typically, it will be a three-step transformation of some kind, and the reactions can be done in different orders, but there are three fundamental reactions that a student has to do. One of them is to make this kind of hippuric acid here, and there have been some interesting publications recently about doing this type of chemistry in greener solvents, and one of them is 2-methyl tetrahydrofuran. That is viewed as a greener solvent because it's indirectly derived from corn cobs. This is not overly expensive as a solvent. It's certainly possible for students to use this in an undergraduate lab as an alternative, and the reaction that they need to do works quite well in this kind of solvent. We give them 20 millimoles of the starting material and just say to them, that's all you're getting. You have to work with that and plan your work accordingly. And we see how people do in terms of their synthesis. Another example of what people have been doing historically with this experiment is to use a catalytic strategy for the final step, and that is typically then taking this kind of hippuric acid and condensing it with an aromatic aldehyde. And there's nice literature, research literature, where this has been done with a bismuth salt of some kind, bismuth triflate or bismuth nitrate particularly. It turns out that bismuth salts are incredibly non-toxic, and if you look at the actual LD50s of them, you have similar values to just common table salt. They also are not very expensive to buy, and they're used in small quantities because it's catalytic. And this will form the azelactone typically very nicely, no matter what the substituents are on the two aromatic rings that you're incorporating into the final product. So it's quite nice to see students working and designing their own projects there. Just a little bit of information on how we tie this in with the lecture material, because I've spoken entirely from a lab perspective. As I said towards the beginning today, we design the lab really first, and the lectures fit in around the lab. So green chemistry is a common thread throughout the 24 lecture hours. And you can see that a number of the topics there feed in directly to what's going on in the lab in terms of green metrics, using alternative reagents and solvents and so on, all the mechanistic aspects of the catalysis. Also, we take some time to go through some detailed industrial case studies where students learn about how Viagra is made industrially, for example. We take examples from the President's Green Chemistry Challenge Awards that are updated every year, and they have very real-world relevance for the students, and they can see the real point of doing the greener reactions in the lab. We find that Organic Process Research and Development is it's an ACS journal. It's an excellent one to get recent industrial examples from in terms of green chemistry, because the sort of process chemistry that is described in there is very much green chemistry. So that's a nice resource. This is just a slide taken from from a lecture that is shown to undergraduates in the context of Viagra. So we just show them simply how the medicinal chemistry route has changed from the amount of solvent used from the medicinal chemistry route back in 1990. Pfizer were using over 1,000 liters of solvent to make a kilogram of Viagra, and the majority of that was dichloromethane, the bigger orange bar there. It's gone down to, or it went down in 2004 to about 7 liters per kilogram, where the solvent composition had changed. Not only has the amount of solvent gone down, but the solvent composition has changed quite dramatically. And the future target back from 2004 was to get to 4 liters per kilogram, and I'm sure they're there now, or they may be doing even better than that. So that's a nice example for them from an industrial perspective, and there are other aspects to the Viagra synthesis on top of that one than just the solvent usage. We use this course, Organic Synthesis Techniques, within a program that we started about 3 years ago now, called Synthetic and Catalytic Chemistry. So this is an unusual type of program. It focuses on a lot of green chemistry in the context of different courses, not just the one that I've spoken about with you today. The course that I have spoken about is the capstone course in the program. There are other third-year labs in inorganic, physical chemistry, and so on required. There's a research component to the course, and from a catalysis perspective, this is something that we put in the lab manual. This was said by Alwyn Mitash, who was involved in the Harbour process and the design of catalysts used to make ammonia a long time ago now. He actually said back something like, it was quoted in J. Chem Ed in 1948, but he said it before then. Chemistry without catalysis would be a sword without a handle, a light without brilliance, and a bell without sound. That's from a while ago, and it's interesting to put that into perspective now with all the interesting catalytic reactivity that is in the literature. Just to finish up, because I know that we are going to allot some time for questions. Bob mentioned this in the introduction today, a green chemistry textbook. This is actually in your library, I think, in the Oppenheimer library, and I'm very appreciative of that. It's called Green Organic Chemistry in Lecture and Laboratory, and I edited this. It was published towards the end of August last year. I contributed one chapter, and there were 7 chapters written by other people, all from North America, primarily actually from Canada, but a couple of authors from the US contributed chapters as well. Somebody particularly wrote a very nice chapter about microwave reactivity and how industrial microwave reactors can be used within an undergrad lab context. There's chapters on solvent-free reactivity, reactions in water, using alternative reagents, and it really tries to summarize what's been done in the last 10-15 years with the idea of encouraging more instructors to put this kind of chemistry into their labs. And even for people that are currently doing it, it will be a nice resource for them as well, hopefully. So it's in your library. If you're interested in this sort of stuff, then take a look at it, and hopefully you'll read some stuff in there that's interesting and useful to you, not just from an undergrad teaching perspective, but just from a green chemistry perspective right across the board. So I think that's probably it for the formal slides that I wanted to show you, and I would be very, very happy to take questions, and I can certainly stay after the hour to try and answer questions from you. So thank you very much for your attention today.
Okay, let's have some questions. Tito, when we hand you the microphone, please keep it about 3 inches from your mouth so that we can pick it up. And please introduce who you are so Dr. Hicks knows who he's speaking to. Thank you.
Hello, Andrew. My name is Tito Viswanathan. I teach organic chemistry here.
Hi, Tito.
Hi. As far as the Bonelli reaction, I don't know if you're aware that you could just mix the 3 components and just grind them together in the presence of paratoluene sulfonic acid.
Yeah.
And you can get almost like 90% yield.
Yeah, we tried that, and we got a pretty good yield. We didn't get that kind of yield. We got a pretty good one. Certainly, yeah, I've seen that in the literature.
Yeah, and the article is written by A.J. Bose, B-O-S-E.
Yeah, I've talked to him about that.
Tetrahedron letters.
Yeah.
And he has a list of compounds, and he's reporting very high yields and high purity.
Yeah.
So that's something to consider.
Yeah, it is. Yeah.
The other reaction where you oxidize the allylic alcohol to an aldehyde, the oxidizing reagent that you use is pretty exotic. You're mixing a lot of things. I'm wondering if you can use a simpler oxidizing agent, a milder oxidizing agent, and convert it to an aldehyde.
Well, what was you suggesting there?
Well, to start with bleach.
Yeah, we looked at the bleach. There are a number of bleach methods out there in J. Chem Ed, I suppose. I don't know if are many of them catalytic.
It's not a catalytic reaction, but
yeah,
it's green.
I mean, I think what we really wanted to try and focus on more than anything else was the catalytic angle. So that's why we went with TPAP. And for a number of years, if I just try and find the slide, for a number of years, we did actually buy the TPAP when our course enrollments were quite small. But then we discovered that it was very, very cheap to make and very, very easy to make. So there's no specific reason why we use that other than it's a catalytic method, really. And as I mentioned, we use it in the context of saying, well, there are green aspects to it, but there are some very non-green aspects to the synthesis too. So the bleach oxidation would probably work, I think.
Okay. You know, the main problem that we teach organic chemistry in 2 semesters.
Yes.
The first semester we do some technique experiments.
Yeah.
And most of the semester is over, and so we just do a couple of more experiments after that.
Right.
Once we teach the techniques like recrystallization, melting point, distillation, fractional distillation.
Yeah.
So what we really need is a textbook that will describe green chemistry with the synthetic with the techniques. Like if you're doing distillation, we need a green aspect to it, so that we can teach green chemistry at the same time that we are doing the techniques. I haven't seen that yet. I think that's what is needed if you're going to sell more books.
Right. Yeah. No, I understand. No, that to my knowledge, there hasn't been a book like that published where the whole book has been green and it's very much built. Right. The techniques are built into that.
Yeah.
I mean, obviously, Doxey and Hutchinson's book is out there, and that has some very nice experiments in it.
Yeah.
But it's not a techniques book.
Right.
It's kind of designed to be used with a techniques book.
Because I see that you started saying organic synthetic techniques.
Yeah.
Okay, but it's many of the techniques are not green unless you do those particular experiments. And these are not. By the time students do this, they are in second semester organic.
Right.
They're not in first semester organic. So we need something green in the first semester organic.
Yeah, I don't disagree with that. I mean, I think that would be a book for the undergraduates could use. The one that I've mentioned here today is not really for undergrads, in the sense that there aren't experimental protocols in there. Because my sort of experience with this is that you very rarely follow a procedure from a lab book. You have to sort of tweak it for your own institutional requirements and the sort of glassware and so on that you have at your own school. But no, there could well be a market for that, the type of book that you describe.
Something for you to consider.
Yeah. Well,
okay, thank you.
Yeah, thank you.
Hello, my name is Josh Moore. I'm a PhD student.
Hi.
My first question is actually kind of stupid. It's on slide 5. Did I miss a joke? I don't really quite understand how that picture correlates to what you're talking about.
Oh, I'm sorry. Yeah, I didn't talk about it at all. It's just an advertisement for sunscreen.
Oh, okay.
It's an older advertisement for. It says here, tan don't burn, use Coppertone.
Oh, well, the people beside me telling me that I'm too young to know that picture. So that's why I didn't recognize it.
I didn't refer to it. So yeah.
Okay, my other question is kind of more general.
Okay.
I noticed you were talking about you want to make things greener, so you're trying to reduce side products and stuff like that. But there are a lot of good side products that end up helping us. You know, like antifreeze, for instance, was something that we found by accident. So do you not worry that the greener that we go, we might actually miss something that we could have just randomly discovered?
No, I think that's a great point. And that's why people have said to me previously, do you want to do everything green? You know, do you want to make your lab, you know, as good as you can kind of make it without it being perfectly green, because that's not really going to happen. But it's very good for students to see things and think about the improvements that can be made and to realize that, you know, there can be, as you've mentioned, serendipitous sort of discoveries and byproducts being very, very interesting and so on. So I think we got to be careful with how green we go. I think people can actually do that with an existing curriculum if they just take the time to look at the experiments that they're currently using and just emphasize greener and non-greener points to students. So one thing I've said to people before is that you don't need to, if you don't do any green chemistry in a lab, you don't need to reinvent the wheel to teach it. You don't need to have a whole bunch of new experiments. You can actually work with what you have and just reframe it. No, that's a very good point that you've made there.
Hi, Andrew. My name is Onindo Ghosh, and I teach inorganic chemistry courses.
Okay.
So I was wondering, can you send me some of your slides?
Of course.
Yeah, I mean.
Yeah, no problem at all.
Okay, thank you very much.
The thing to do would probably just to send me an email.
Sure, I'll do that.
I'll write back to you with the PDF slides.
Okay, thank you.
So you said you were an inorganic person. There's inorganic is not as developed a field in terms of teaching green chemistry.
That's right. Right.
There are some examples in the pedagogical literature, but the bulk of it has been done in organic, as one might expect. But yeah. I think there's a real opportunity for inorganic chemists to develop that branch of chemistry in terms of doing things in a greener way. So
actually, I use like 2 green chemistry experiments in my inorganic chemistry laboratory. Okay. One is use of carbon dioxide as a solvent to do catalysis. Basically, we do biodiesel synthesis.
Okay.
And we teach like turnover number, turnover frequency.
Okay.
And another thing we do is like use of CO2 as a reagent and to you incorporate into epoxide mixed cyclic carbonate.
All right. Okay.
And that we also do it in CO2 as a solvent, and it's a 100% atom economic process. So these 2 experiments, I do it in my inorganic chemistry laboratory.
That's fantastic.
Yeah.
What can I ask? What year that's in?
I'm sorry. This is like inorganic 2.
Okay.
I mean, it's like a little bit advanced level inorganic chemistry students,
so
actually.
Is that 3rd-year undergraduates?
Yes, kind of like that.
Okay.
Yeah.
Okay.
Yeah.
Oh, that's great. That sounds really good.
And thank you. One more question I have: that what is the primary oxidant are you using that geranyl oxidation?
What is the primary oxidant?
Yeah, I mean, is that NMO like?
Well, the NMO is there to shuttle the reduced ruthenium back to the oxidized ruthenium.
Okay. So that's the primary oxidant, right?
Yeah. As I think I said, people have tried that with molecular oxygen, which would obviously be really nice.
Right.
We've tried that and it
doesn't work very well.
It didn't work. No, we took a publication, a J or Chem publication, I think it was, and we tried it in the sort of development stage, and it never got to an undergrad lab. We couldn't get it to work well enough. So yeah.
How about like peroxide or other things? I mean,
that actually may be in the literature. We haven't tried that, but that might be an alternative for sure. Yeah.
Can I make one quick thing? Some people have a class at 2:00 and they need to leave, and Dr. Dix is available for the next half an hour, and he can talk with anybody. So why don't we thank Dr. Dix, and then if anybody would like to continue, please continue. So we have some more questions for you.
Okay, thank you.
So please continue, and we have some more people who would like to ask you questions.
Right.
Or I just have one more question. Like, how do you separate the zinc chloride and in the Viginelli reaction?
Okay, yeah, I didn't say anything about that. So what we do with that reaction under solvent-free conditions, if you just sort of heat the reactants for sort of 20 minutes, something like that, you get a very hard white solid formed, which if you grind it if you add water and you grind it, can be filtered off. And then if that is washed, not recrystallized, but just washed with water and with ethanol, the water takes out urea and the zinc chloride, and the ethanol takes out some organic byproducts. Then it's nice and pure. The NMR spectrum that I showed you a little bit earlier was from that kind of workup. So they're actually quite difficult compounds to recrystallize. They're not soluble in many solvents. But we've never actually recrystallized them. We just wash them.
Thank you. Thank you.
Okay.
Hello. My Hi, my name's Darren Jones. I teach organic chemistry here as well.
Okay.
One thing that I'm interested that I think is kind of a green thing that I've been thinking about personally is photochemistry.
Yeah.
And, you know, like there's that old classic experiment. I think you take like benzaldehyde and isopropyl alcohol and set it in the sunlight and you make an acetylene essentially, right?
Yeah. Yeah, that's right. Yeah.
So my question is, you know, in practical terms, you know, you need a lot of expensive things to do photochemistry, like sometimes special lights, special types of non-unfiltering glass, you know, like quartz or whatever.
Yeah.
But is there a way of, you know, where you can get beyond these ruthenium and rhenium catalysts that do the energy transfer for you to do something in a more green fashion that's more applicable to the organic classroom?
Yeah, that's a good question, and we need to do. When I was researching the book that I mentioned there, at the back there's a big appendix of greener approaches to do fundamental functional group transformations. I couldn't find hardly anything in the pedagogical literature on photochemical reactions. So I think your point is a good one and an important one. There are a couple of examples of some cycloadditions, I think, that one that Doxey and Hutchison in their textbook reported. I can't remember the details of it right now, but I think the ones that have been published they're slow reactions. They've been done in sunlight and they're slow, so obviously that's not so advantageous from an undergrad lab perspective, and you know, you need sort of sunnier climes to do that sort of chemistry. But there's certainly an area that could be exploited some more, but it's hard. Yeah, it's hard to see what sort of reactions would fit nicely into there.
I mean, the nice thing about that photochemistry stuff is so simplistic to set up.
It
you
is.
Stick the two things together. There's no heating, all that kind of stuff. It's just shine a little light. It's just that it's impractical.
Yeah.
In the classroom, because
right.
you know, you have 2-3 hours,
Yeah.
and it needs to sit there for an extended period of time typically.
Yeah. I guess if you excuse me, if you have a reaction that can take a week, you can probably store it somewhere.
That's right. You're like on the windowsill out in front of the light. Yeah.
That's right. But I mean, we often as instructors want to get things done in sort of a 3-hour period, don't we? And not everyone has that storage.
Well, and not only that, our building's built in a fashion such that usually it's the sun comes in from the south side, and our building faces the windows are on the east and west side of the lab. So you only get the western sun when it's setting, which might not be the most intense.
That's right. Yeah, that's right.
I really liked your talk. Thanks a lot. I really appreciate it.
Okay. Oh, I'm glad you did. Thank you. Well, thanks for coming. It's much appreciated.
We all really appreciate your time, Andrew. Thank you.
Okay.